we are on to next lesson. So this is B. It's a little blurry. Hold on. There we go. That's better. So hopefully you were able to do the activity, our sample to sampling activity. I'm going to refer to it sometimes during this. So if not, and you get lost, come find me and we'll talk about it. So what we're talking about here is sampling variability. So why does one sample look like the other, and how can we make some inferences on that, and what can we all put together? So when taking a sample and gathering sample proportion, we know it will not exactly be equal to the population proportion due to sampling variability. So we have this natural variability in samples. So for example, we know that we had a sample size in our card activity, we had a sample size of 100. And we said we had 50 checks and 50 X's, and ideally our proportion of success would be 50%, right? 1 out of 5. However, we saw sometimes we would get 2 out of 5, or we would get 3 out of 5. Actually, we were doing sample sets of 10. Hold on. So we would have, well, let's just do that, 2 out of 10 or 5 out of 10. We didn't always get 50%. And the reason for that is because of natural variability. So let's talk about all this vocabulary. That's what this first page is here. We're talking about this vocabulary, and then we're going to talk about how that affects our sampling distribution. So what happens is we have this population distribution. And population distributions means we have one population distribution. So on this side, we see here we have successes and we have failures. So this is categorical. We have a success, we have a failure. This one, it's kind of hard to see. So I have 140 successes, and that value there is 260. So my total population size, capital N, my total population size is 400. And if I look at my proportion or probability of success, I got 140 out of 400, which is 0.35. So my proportion of success, my P here, proportion of success, is going to be 35.35. Now, this is a sample distribution. So if we look at this in terms of the cards, over here we had 100 cards, and we did a sample. In our sample, we pulled 10 cards, and we saw, was it a check or was it an X? So we can have many different sample distributions, and each sample distribution contains a p hat. So here's our p hat. Think back on when we did regressions, we had y hat. Well, now we have this p hat. And so this p hat that we have here is our proportion of success. And if we look at this one, we have a total of, let's see, this is 18 and this is 22. So our sample size is only 40. And our proportion of success is 18 out of 40, which is going to be 0.45. And just looking at these two bar graphs, that makes a lot of sense because this is higher than this one. So we would expect this to be a higher proportion. Okay, so what we do is we have this overall population distribution and we have this sample distribution. So I'm going to add a couple of things on here. If we looked at the mean, when we were talking about population or proportions, we used mu as our mean. And when we talked about standard deviation, we used sigma. So when we did this in terms of a random variable, we would say u of x and sigma of x, right? Well, when we look at just a sample, we have a sample here. Now our mean is going to be x bar. And our standard deviation, this goes all the way back to unit 1, our standard deviation here is just a small s. So we get these values right from the calculator when we use our VARS capability. So we have a population. From the population, we pull one sample. We've got this one sample, but we know that there's natural variability, so we want to take many, many, many single samples and create something called a sampling distribution. So the sampling distribution is going to be all samples together. And we only have one sampling distribution. So the sampling distribution takes all possible p-hats, so every one of these individual samples that we have, and takes the values from every single one of them and creates a sample distribution of the same size n and puts it together. So what this is saying is all of this shape of this new curve is a bunch of samples of 10. Oh, sorry, this is 40. So this would be samples of 40 from this population of 400. We put these all together and we get this unique sampling distribution with the same common properties that we would have from our population distribution. So this models this value very similarly because we've taken a lot of different data. And we see that actually right here. So if we look at this data, the mean that we have, the center of this distribution is 0.35, which is what we had up here as our proportion of success of our whole population. So how do we account for that? Now what we're going to do is we're going to take some of this nomenclature and some of this nomenclature and put it together. So if we want the mean of a sampling distribution, we're going to say the mean of p hat. So remember up here we would say the mean of x, so the mean of our random variable. Well, now we have the mean of our sample sets. And now this number becomes quantitative. This is categorical, success, failure, and down here we no longer have success, failures. Now we have this probability curve where we have the mean of our proportion of successes. So that would be our p hat. And then our standard deviation is the same thing. We have a big standard deviation here of p hat. All right, so that's kind of some vocabulary of how these three things are going to come together. We're going to spend the rest of today talking just about sampling distributions. And then we're going to come back to this standard deviation here in just a few minutes, okay? All right, so now that we created this distribution, we're going to talk about the distribution, and we're going to talk about it, we're going to describe it the same way we talked about distributions back in chapter 1. And we're going to use this SOX anagram that we had here, and that is shape, outliers, which in this case we're going to ignore, center, and spread. And remember, our spread here is our variability. Okay, so we're going to start with center. I know it's not our first, it's not our shape. We're not starting with the first one, but with these notes, it started with sampling, started with center, so we're going to go with that. Okay, so when we start taking samples of a population, we have to revisit an earlier question: how trustworthy is the statistic at being an estimate? And what that's saying is, if we pull together this statistic and we know that we've got good data in this, then ultimately what's going to happen in our sample distribution is we're going to end up with this normal curve. But if this sample data is not good, then this is not reliable, and we can't pull data from that if it's not reliable. So what happens is a sampling procedure is bias. So remember in chapter 3, we talked a lot about being biased. If it tends to systematically overrepresent or underrepresent a population, okay? So to avoid biased samples, we want to make sure that our samples use random, I'm just going to say uses random, because it's either going to be an SRS, simple random selection, or it's going to be random assignment. And we would use random assignment for an experiment. We use random selection for anything else. All right? So a statistic used to estimate a parameter is an unbiased estimator. And this term estimator is new, and so we're going to spend a little time on this little activity here talking about this estimator. Now, what happens is, if we have an unbiased estimator, so if it's unbiased, then we can go directly to this. We can say that the mean of that proportion is equal to our population parameter. And this is what we want to do. We want to prove that it's unbiased so we can go directly to this number. If I flip this over, we see that the mean of our sampling data is 0.35, and the proportion of success in our population is 0.35. So we want to not have to go in and calculate all this data. We want to just be able to go straight to this and say, okay, because we proved this, we're going to use this proportion of success from the population. All right? So what does that look like? So here's an example that I found on College Board. It says a breeder has 5 dogs. A sample of 3 dogs will be randomly selected for a study. The ages of the dogs and the years are here. So we have a puppy and we have a 10-year-old dog. Okay, so the question says, is the sample mean an unbiased estimator of the mean age of the population? Okay, so what this is saying is the sample mean, so is this an unbiased estimator of the mean age of the population? Does it equal this? Okay, so we have to determine this estimator here. What does that look like? So I have these population ages, and the mean of these population ages is 0.5. So when estimating a parameter, the estimator is unbiased if, on average, and this on average part is important, the value of the estimator is equal to the population parameter. So our population is small enough that we can actually test it. And so we're going to test it on this one so that you see how this works. So we have these different ages. We know that our mean of this is 5. So one possible example of a sample of these 3 dogs' ages is 0 to 5. So if you used an SRS and you pulled this out and you got 0 to 5, you would get X bar. So remember, this is a single sample here. That's why we're using X bar. So the mean of this single sample would be 2.3. So a sample statistic is a point estimator. Point estimator of the corresponding population parameter. Let me read this again. A sample statistics, that's what this is. Sample statistic is a point estimator. I have one sample point of the corresponding population parameter. Now, these two values are not equal. This is a single value. We know there's variability in a single sample. So if we go down here and we run every combination that we could get and we put these on a number line, we see as we put these on a number line, they fall above and below our mean, our population mean, which is 5. And so what happens is when you do the math on this, of these values that we have, we find that the mean of X bar, so the mean of all of these individual samples, is 5. So what happens is when estimating a population parameter, an estimator exhibits variability that can be modeled using probability. Now, lots of words there, but this is what this is saying. Remember, this is a point estimator. So it says an estimator exhibits variability. We see there's variability 2.3 to 5. So we have variability, but we model that with all of the different types of combinations that we have. And this is going to be an estimate of the population parameter, which we already said was going to be 5. Now, when we do all of this, when we do all the math of this, we find that the population parameter models our sampling, all of these different samples. So it models it so that these two are the same. So because they're the same, we're going to say it's an unbiased estimator. So let's do, which is what we wanted. Remember, unbiased estimator says that these two values are going to be the same. So let's look at another example. So here we're going to look at the example of range. So we have a puppy, we have a dog that's 10. So the range that I have here is going to be, my population range, let's go back up here. My population range is 10. So if I take one sample of the dogs, this range is going to be 5. So this is my point estimate and my estimator, right? So if I look at this value of range, it's asking, is the sample range an unbiased estimator? So we want to just look at the same thing that we just did on the other page. So I look at all of my combinations and I'm looking at the range. So 0 to 5 is 5, 0 to 10 is 10, 2 to 10 is 8. So I come up with all of these different points and I can put them on a dot plot right here. And when I go in and I look at the mean of these ranges, if I was to plug all these in and run one vars, I would find that my mean of the ranges is 7.8. Well, 7.8 is not equal to 10. So notice that the different values of the range for the different samples of size 3, so 3 data points, vary, but they do not vary on either side of the population. They only vary on the left side. So here's what we expected. So we expected to see variance on this side and on this side so that my average would be 10, and that's not what happened. So an estimator is, an estimator is unbiased if on average the value of the estimator, and this term estimator, this is just what you're searching for, right? So here we're looking for range. So the point estimator here is range, and on the other one we were looking at mean, right? So it's really, the estimator is just a fancy word for what are we searching for. It's not a random variable, it's just something that we're evaluating. So this estimator is equal to the population parameter. So estimator's unbiased if the value of the estimator is equal to the population parameter. Here, for this example, on average, the value of the estimator, and I'm going to just change this a little bit, because here the value of my estimator, what I'm looking for here is actually the range, does not equal the population parameter. And I'm going to add another word here, population parameter for range, right? So we're comparing the range here, which was 10, to our overall sampling estimator, which is 7.8. So in this case, the range is a bias estimator of the population range. So because this is bias, if we go back up here to our center, we can't use this, and we can't say that the range, which was 10, is equal to our population. We can't say this, right? Like we can for the mean, but we can't for the range. So let's talk a little bit about shape. So the shape of the sampling distribution. So no matter the shape of the population distribution, so shape of the population distribution, this means that it can be skewed, it can be bimodal, it can be symmetric, it can be normal. Any of the different shapes that we've had doesn't matter. No matter the shape of the population distribution, the shape of the sampling distribution will always be approximately normal as long as a condition called the large count condition is satisfied. Now, what this is saying is if we have a lot of data over time, that data is going to give us this approximately normal curve. Well, when we don't have a lot of data, we use this large counts condition, which we're going to call the central limit theorem. And the central limit theorem is a formula that we're going to say NP is greater than or equal to 10, and N times 1 minus P is going to be greater than or equal to 10. So both of them are going to be greater than or equal to this value of 10. Now, what is this? So this is my sample size times my success. And this is going to be my sample size times my failures. And in both cases, sample size times success, sample size times failures, both of these have to be greater than 10. If this happens, we can say that the distribution will be approximately normal. And note here it says never just say normal. We always have to say it's approximately or approx normal. And so this is because of something that we're going to call the central limit theorem. We're going to spend more time on this later, but right now just know that this large counts condition basically says that the sample times the number of successes is going to always be bigger than 10, right? Or sample times number of failures is always going to be bigger than 10. Okay. Now, when this happens, when we can say that this is true, we're going to get an approximately normal curve. So that's going to affect the shape of our sampling distribution. Okay. All right. So now let's talk about the last thing that we need to talk about here, and that is the spread of the distribution. So what happens is, as we have this, it says the statistics will vary from sample to sample due to sampling variability. We've talked about this. However, larger samples have less variability than smaller samples. We've talked about that. The spread of a sampling distribution does not depend on the population size, but instead depends on the sample size. So we just said that over here. So as we look at the shape of this, we're looking at our sample size times successes. It doesn't matter what our population size is. We're looking at our sample size. So over here, we talk about sample size again. So for independent samples, and this is, we've got two things we're going to talk about here. So for independent samples, it says sampling without replacement. We have, this comes from your AP formula sheet. We have our standard deviation. So standard deviation of our population, we use this formula of P times 1 minus P over our sample size of N. Okay, and remember, this right here is our sample size. So if we have this without replacement of a categorical variable, we know that this is what we end up with. Now, if you remember a minute ago, I said we can test this on the very first page of our notes. So very first page of our notes, we said that our standard deviation was 0.0754. So what I know is that my success success probability, sorry about that, success probability is 0.35. So if I plug this in, I'm just going to go down here and plug it in for this example. I would say that our standard deviation of P hat, so of our sampling distribution, is going to equal our success, which is 0.35, times the failure, 1 minus 0.35, all over our sample size. And our sample size, if we go back to this example, our sample size over here was 40. So we put this value of 40 in here. And what we get is square root of 0.35 times 1 minus 0.35 all over 40. We get this value here of 0.0754. And that's where this value came from in this normal curve that we had. So we have something sampling with replacement. So for example, we pull something out, we put it back in. So with replacement, we're going to use this formula. Now, what happens if we're sampling without replacement? So this is like what we did in our simulation activity with our cards. We pulled those out, we didn't put them back in. The standard deviation of the sampling distribution will be slightly different. However, as long as a special rule is followed, the difference is negligible. So we're going to use the same formula if this 10% condition is met. Now, what the 10% condition says is we don't have to worry about replacement, which means we're not, so if we pull things out, eventually we would run out of things, right? So if we kept pulling cards out of the cup, eventually we're going to run out of cards because we're not replacing. But if we sample without replacement and we have a big population, then technically we're not going to run out, right? So we have this 10% rule, and what this 10% condition says, it says N is less than or equal to 10%. So remember, N is your sample size. Now, a better way to write this is that n is less than or equal to 0.10, so 10% of big N. And this big N is going to be your total population. Now, let's go back to this dog example right here. So I have a sample of 5 dogs. This is my sample set. I have 5 dogs. And I took samples of 3 dogs. Well, if I wanted to look at something like this, my sample is 3 dogs, and that value is going to be less than 10% of the total population of dogs, or even the total population of whatever this is, Weimaraner dogs, whatever those are, right? So I don't know, let's just say there's 100,000 of those guys. So if I take 10% of 100,000, that is going to be much larger than 3. So we can use, for our spread, for our standard deviation, we can use the same formula that we have up here if we meet this 10% condition. And that is sampling without replacement. Okay, so it's important that we understand, depending on what it tells us, that we have to prove this 10%. We have to just state on here. So it says, if a problem does not mention population size, we want to describe N with words that will assume it's large enough. So all dogs in the country are going to be much bigger than our sample size of 3. Okay, now, this is important down here. It's only important to note that you need to check the 10% condition when you're sampling from a population. If you have an experiment, you're not sampling. All right, so let's put this all together. What does this look like when we put it all together? So we have a problem here. It says, a recent study looked at the percentage of young adult women who get less than 7 hours of sleep a night. In the study, they say that 45% of the women get less than 7 hours of sleep. What is the probability that a random sample of 50 women will result in a sample proportion of 50% or higher? Okay, so we're going to do the same thing that we did earlier. We're going to communicate, we're going to create and calculate, which is a little backwards from what we were doing earlier, and then we're going to go down here and do conclude. You'll see how these 4 things are all going to come together. So first thing that we need to do as we have this in is we have to define everything that we have. So if we look at this, I'm going to say that my probability that I'm looking at here, this P, is going to be the proportion of women who get less than 7 hours of sleep per night. Okay, so that's the parameter in the context of the problem. That's what we're looking for. Write down the probability you were trying to find. What I'm trying to find, the probability here, is that my p hat, right, my p hat is my sample, is going to be greater than 50% or higher, so greater than or equal to 0.50. This is what I'm looking for. What is the probability that a random sample of 50 women will result in a sample proportion of 50% or higher? So here's what I'm looking for. Okay, so it says create your sampling distribution by finding the center, spread, and shape. So to do this, center, spread, and shape, I'm going to lock this into 3 different things. The first thing here is I'm going to use this word random. So if it's random, if we go back to what we said about our center here has to be a random sample. It has to be an SRS. We have to have a random sample. So if I look at this, it says probability that a random sample of 50 women. So we already know that it says random sample taken. So because a random sample is taken, we can say that the mean of p hat is going to equal that population parameter, and that population parameter was 45%. They say 45% of women. So my population, my mean of my p hat is going to be this 45, which is my population parameter. Okay, so the next thing I have to do is I have to check, is it independent? That's the next thing that I'm going to look for. So if it's independent, I have to check and make sure that this meets the condition that it's my sample size is big enough. So it says here that I want to take a random sample of 50 young women. So I have 50 young women, and this has to be less than or equal to 10% of N. And N here is going to be all young adult women. So because all young adult women is going to be a very large number, I can assume independence. And so because of that, I can use my standard deviation. So standard deviation of p hat is going to tell me that I have my proportion of success, which is 0.45 times 1 minus 0.45 over my 50 random women. And when I plug this in, I get this value of standard deviation of 0.0704. Okay, last thing that I'm going to check here is this normal? So I need to know, nowhere up here do I see that it says I have a normal distribution anywhere. So I have to check this. So for me to check this, for normal, I'm checking central limit theorem. So if I'm checking the central limit theorem, that says my population size, let me just write this over here. So this is N times P is going to be greater than or equal to 10, and then N times 1 minus P has to be greater than or equal to 10. All right, so I have 50 times 0.45, and that has to be greater than or equal to 10, and then I have 50 times 0.55, so 1 minus 0.45 is 0.55, and this also has to be greater than or equal to 10. So what I have here is N to P, so this is true. So because these are true, this is also true. If I plug this in, then I can assume approximately normal. All right, so I have to go through. I'm going to go ahead and label these. We're going to check for random simple sample simple random sample is going to give us our mean. Independence, which is checking our 10% condition, is going to give us our standard deviation. And central limit theorem is going to tell us if it's normal. Those three things. So now we're going to move over to our calculate. So again, I'm just going to state this. The probability that we're looking for here is greater than or equal to 50. So because I know this data up here, I can say that this probability is going to be approximately normal, and my average is 0.45, my mean is 0.45, and my standard deviation is 0.0704. And I'm pulling this directly from this data that I have right here. So now I can go in and I can look at my z-score. So my z-score, is that going to be greater than or equal to, if I'm looking for 0.50, remember up here I want to know 50% or higher, so this value here, oh, this should be 0.50, sorry about that. So 0.50 minus 0.45 over my standard deviation of 0.0704. So when I plug this in, what I get here is that this probability that the z-score is greater than or equal is 0.7102. All right, I'm going to go ahead and draw this. I know this says that drawing the curve is optional, but I'm going to tell you that that's not the case. You need to draw this curve. So this is 0, this is 1. So what I want to know is this value right here, which is 0.710 and greater. Okay, now I'm going to use normal CDF, and I have my lower bound is going to be 0.710. My upper bound is going to be infinity. My mean is 0, and my standard deviation is 1. So what I get here is that my value is 0.2389. All right, my conclude. So my conclude is going to be the probability that a randomly selected woman from a sample of 50 women, resulting in a sample proportion of 50% or higher, lots of words, of women who get less than 7 hours of sleep is 0.2389. And I'm sure some of you are much more gifted at speak than I am, and so you might have come up with a better way to put all of that. But what's important is that we talk about that we're going to select a sample of 50 women, so a sample of 50 women, that's important, with a sample proportion of 50% or higher, because that's actually what we were looking for, of women who get less than 7 hours of sleep, that's the context, is 0.2389. Okay, you know what? I'm going to go ahead and stop it, and you try this one on your own, and then I will post my notes, and you can check the answers for this one.